today for this colloquium in association with WCRP My Climate Risk. And the title of the talk is From Adjoint Sensitivity to Data Assimilation, a Perspective on Indian Heat Waves. And let me share a bit more information about him. He worked as a doctoral researcher at the Potsdam Institute for Climate Impact Research in Germany and holds a PhD in theoretical physics from the University of Potsdam. His expertise lies in the applications of advanced statistical tools from nonlinear dynamics such as recurrence quantification analysis, complex network theory, and extreme events theory for understanding climate dynamics. And currently, his research focuses on coupled data assimilation, adjoint sensitivity analysis, decadal prediction, and disentangling the causal mechanisms driving climate extremes such as heat waves and extreme precipitation events. So thank you for agreeing for the talk and welcome to IITM.
It's working, right? So, okay. Good morning, everyone, and thanks, Dr. Aditi, for your kind introduction. And I am very happy to be here at the big campus of IITM. I lost myself twice, so that's a good start. And is that I'm also excited to share our work on data assimilation and adjoint sensitivity using an intermediate complexity model, CISM. So before diving into the details of my talk, so let me tell you briefly about our group at the University of Hamburg. So I am a second-year postdoctoral researcher under Professor Detlef Stammer, and our group is called CISM Group. It's called Center for Earth System Assimilation Model, and that's the picture of Hamburg as a nice port city in north of Germany. It's very beautiful in summertime, but not good in winter. So I am here always. And that's our office, and this is our building, and this is we also share with Max Planck Hamburg, and that's our group. So my project or my task is basically to do coupled data assimilation. So I'll share a bit more insights on this data assimilation and also coupled data assimilation in my talk. So that's the outline of my talk. So I'll explain about the CISM, the model we use in our institute, and also the 4D VAR assimilation, or a variational assimilation perspective, and also how we can use the adjoint sensitivity to understand extreme events, for example, Indian heat wave. So we have this model coupled with an atmospheric model called PLASM, which is also developed at the University of Hamburg, which is an intermediate complexity model and has this two resolution, T21 and T42 is a truncation. So T21 is basically around 5.6 degree the horizontal resolution, and then we have 10 vertical levels. So it's mainly the troposphere we have in this atmospheric model. And then we have MIT GCM, which is coupled with this one. So in MIT GCM, we also have this two resolution, this 90 cross 44, and then we also have this 1 degree model. And we also have two configuration, 15 and 23 levels. And this CISM comes with an automatic differentiation, like a TAF, which develops the adjoint model. So there are two models we have. One is the adjoint forward model, which is called CISM, and then we have CISM adjoint. So that's how we use these two things to carry out all kind of experiments. So this is the climatology of CISM. So it's a very almost 1 degree or 2 degree in the atmosphere and 1 degree in the ocean. And you can see the mean climatology, mean state of SST. This is SST bias I'm showing. So in SST you have more or less we have zero bias is good, but in some of the area like this extent and the other parts we have a negative anomaly. So the SST is kind of have a less temperature than the observations or the reanalysis. And in some parts, we have this kind of high positive anomaly. And this could be due to the coarse resolution and also the eddies or the dynamic topography on that region. And this kind of bias is also a bit common in the intermediate complexity models. but they have like few structure which is not the, like we have only this area, but and also like 60 degrees. So that we are trying to resolve in our CISM 2.0. Then we have this sea surface salinity bias. Even you can see like it's mostly on the Arctic, and that we figure it out that it's coming mostly from the freshwater runoff. And that's also like we are trying to do that to solve this one. And if you look into the vertical profile, here we have this like positive bias in the surface level, and in the deeper level we have a kind of negative bias, like in like cold bias in the deeper ocean. And same with the atmosphere. If you look into that, in atmosphere we have here mostly the cold bias. So the CISM temperature is kind of less than the observations or the reanalysis. But if you look at the zonal mean, the profile, they are pretty. This black is the blue is the our CISM, and the black is the observation. But they follow some kind of good approximation in the profile, like the zonal profile. They have it, and we also have this sea level pressure. You can see that they have like kind of very strong, not strong, but they have the large scale connections. It's also there, but we also have bias in mostly in the mid latitude. But in the tropics, you see they have like zero bias. So this is also kind of a good approximation. And also like the zonal mean follow a kind of good profiles and good trajectory. And if we look into the zonal mean temperature and also the wind temperature, the zonal wind temperature, we have like a very good this easterlies, tropical easterlies, and the temperature is there. But we have bias mostly in the tropopause, in the high troposphere. That we have positive bias. And then if you look into the jet stream is bit shifted in CISM. So these are the like configuration or this kind of mean state we have in the CISM, but overall it is a like kind of present a good mean state of the Earth system. And the one thing is very good about the CISM, you can just run on your simple desktop. If you have like 4 GB of RAM and like some hard disks, 1 TB, so it's fine. You can run. It has like 10 minutes. It will compute for 1 year. So something is very good. And we are also trying to improve the efficacy or like make it very to take less computational resource. So that's our aim to like promote the intermediate complexity models. So now, as I mentioned earlier, that my work is mostly with the data assimilation, and in this data assimilation, we work mostly on the 4D VAR. And I'll explain a bit more about the 4D VAR thing. So first, let's go with the data assimilation. Some of you might know about the data assimilation thing, but it's just to have a genetic introduction. It's basically a method to combine the observations with the model state. So we have two things going on. We have like observations. We have from like radar thing or the like satellite. We have ground observations, but these observations are very sparse. Especially when it goes to ocean, it's become very sparse observation, and they also have gaps. They have noise. So it's difficult to analyze this observation, to have like long-term statistic or long-term analysis. To do that, and on the other hand, we have models, or they're like a very high resolution ocean model, like land model and atmospheric model. But these models are good to like present the mean state of the Earth system. But when it comes to like express or when it comes to represent the current state, there we have some problem because we don't know the initial conditions, and we also have problem with the parameterization. So to resolve these two things, we somehow need to merge this observation with the model state, and that's the whole thing called data assimilation. And in the data assimilation, we have basically two branches. One is in the sequential or the ensemble or the filter approach, and other is the 4D VAR or the variational approach. So in the sequential method, what we do, like we first run the model forward. So you have any model like atmosphere or ocean. So you first run the model forward, and let's say you start from 0 to 1, and then you have an observation. So then you compare the difference between the model state or model forecast state and the observation state and see the difference, how much they differ. And then you try to see like, okay, whether you can incorporate that information, like you have like the real world information into the model. To do that, we use like different filter approach, like Kalman filter and ensemble Kalman filter. And this filter approach approach is very much used nowadays, like NCEP, ERA, atmosphere. They all use this ensemble Kalman filter. And though it's a bit computationally expensive, but it's a bit useful because ensemble filter or this Kalman filter, they can handle the sparseness of the data. Now, like for example, the NCEP, they use only the surface pressure to assimilate. So NCEP also has a bias, but it can mimic some good Earth system state. So this is the pros of the ensemble Kalman filter, but at the same time, the filter approach, they are not constrained by the model physics. So there it comes the Forty-Var. In the Forty-Var or the variational approach, what we do, we have a model state. So first we define an assimilation window. So for example, in ECMWF, as far as I knew, that they use like 12 hours or 18 hours, the assimilation window. And then they have their forecast state, then they have the observation state. And they find that they compute the cost in between, like the difference in between model state and the observation state, and they call it cost. And they try to optimize. So they just go backward and then they try to optimize this cost somehow to have a good approximation of the observations or the model state. So I'll explain a bit more about this Forty-Var because we work only with the Forty-Var and we are trying to do some more with the ensemble in future. And the application of the data assimilation is kind of very important. For example, the reanalysis. In the reanalysis, they use the this kind of either filter approach or Forty-Var approach, and it depends like in which aspect you are doing. But in the reanalysis, we use for the data assimilation is used for the creating reanalysis and also like numerical weather prediction and also like decadal prediction. So they have like lots of uses of the data assimilation thing. So how we do the Forty-Var thing? So Forty-Var is basically, I explained with this simple schematic. So first we run the model forward. And when we are running the model, so this is like an assimilation window you consider. And when we start from an initial state like parameter and the initial condition, we are running the model forward and we have our model state, let's say temperature or SST or anything. And then we compute the difference of that particular time window with the observations. So we have like this J is called the cost function. So that's very common term in the Forty-Var. We call like this J, we denote as a J. So once we have this cost function, we see how far or how different they are. Like you can have some is a quantity. So you can see like how large it is, the difference between the model state and the observation state. And once we have it, then we go backward. So we try to go backward in time. So see whether we can manipulate some of the parameter of the system state to have like to minimize the cost. So how we do, and while we are going the backward direction, we always see the gradient of the cost function. So that's the most important thing. So we need to compute the gradient because this will give you the direction, like which parameter or which state you need to optimize more. So it is an iterative process. So we first in one loop we go and we optimize some parameter, and then again we go forward. So it's like it goes again and again. So sometimes it takes like when we do the assimilation, it takes like 1 month or 2 months. So based on your model configuration or the assimilation window. So it's a bit expensive, but the good thing is that when you are assimilating this observation, you are kind of constrained by the model physics. So your model is actually seeing the observation. So to optimize the cost function. So that's why like Forty-Var is very good for the estimating state. Even I guess most of the NWP, they use this short window, short assimilation window to do the forecast. And also it's all very important for the cyclone forecast. I think France, Meteo France, they also do this Adjoint application to do the cyclone forecasting. So that's why it has some good point as well. And here are some mathematical representation how we do the background of the Forty-Var thing. So let's say we have a nonlinear model, this xi or this mx. So let's consider you have Lorentz system. It's a nonlinear system. You can express with some like a very easy way to do that, and that's m is called like nonlinear operator. So you have your current state, you have a nonlinear operator, you can have your future state. But if we have a slight perturbation on the initial state, and that's mainly coming from this nonlinear dynamics. What we do, we find a tangent of that particular point. So this is called like the Jacobian of the system. So you might heard about this Jacobian thing. So we first have this linear Jacobian with a slight perturbation in the state, and that's the whole thing is kind of a tangent linear model. And this is like a cost function we have, where like yi is the observation and xi is the model state, and you have some error covariance. So it's like quadratic cost function you have. And then you try to find some kind of sensitivity or kind of dependence on the initial conditions, because we are trying to see the initial conditions, or you can also replace by the parameters. So it depends, like based on your interest. So once we do that, so we have a very big kind of expression, and you have this M. So all these are metrics. So if you do the TLM, you need to store the metrics again and again and again. So it is not computationally efficient. So just to avoid this part, what we do a clever mathematics. It's called adjoint approach. So I don't have the whole mathematics because it's like 2-3 pages. So it's just like I wrote only the last expression. So you can define some kind of adjoint variable. So this thing is coming from this Lagrange multiplier stuff. This is the optimization problem. You can look into this paper by there's a book by Oliver Talagrand. So there is, if you're interested. So it's a really nice book, and paper. He also has many papers on this thing. So we define the adjoint variable, and now we have like this kind of an equation which are solving from the background way. No, so like now we are trying to go back and see how we can find the state of the parameter. And once we reach to the initial state or the at 0 point, we have this like del x naught. Let's say we are computing the gradient based on x naught or the initial condition. We achieve this lambda naught. So let's say if you deal with the Lorentz system, you have like 3 lambdas, and those are like your adjoint variables, and that you can be a state or parameter or something like that. So, but you can use like other thing as well, like you can use like the boundary conditions, or you can use like your parameter, your initial condition. It depends. And the other thing, so adjoint part I mentioned here. So adjoint is important for the 4D var or 3D var thing. But the other part of the 4D var is that you have, once you have an adjoint model, you can also play with that. Because adjoint model also allows you to do the sensitivity analysis. In the sensitivity analysis, you don't need an observation. You just try to understand, say, for example, you take a mean temperature of Europe or India, and you see the mean temperature of let's say winter temperature, how it is being driven by or influenced by other factors. So you set up a cost, and you try to go back, and you have all the sensitivities with respect to the parameter. So this is a very easy way to represent. Like we have like inputs, you set the inputs, and then you go back, go forward, and while you are going back, you have this this A star, B star. These are your adjoint sensitivity. So you can also do in a forward way. But when you have large system, when you have 10 to the power 7 number of parameter, so you have to change, or you have to like tune the parameter and see how the output looks like. So that's basically the kind of sensitive, how sensitive the output based on your change in your input. So to avoid that part, we can use the adjoint sensitivity, because once you are running the model backward, it will provide you the sensitivity with respect to other parameter as well. So you just run once, but you will get the full configuration or the full output. So that's the good thing, and which because my work mainly with the adjoint data assimilation, but I have strong interest in the adjoint sensitivity analysis, because it's important. Like we have a high temperature or like cold wave or heat wave or anything, we can see the processes are actually which are influencing this kind of phenomena. So, but before that, let's talk about a simplified model. So we have a Lorentz system. And what I mentioned that you have this kind of observation. So these gray dots are the observations going on, and you have a model state. So model also can, like you can run forward, and you start with the initial condition or the initial parameter, and you can just see the how model goes like. So you can see like after a few, the model state doesn't match with the observation state, right? So there the sensitive data assimilation comes into the picture. What do we do? Like we use this adjoint thing. So this is the nonlinear equation you have, And when we do the tangent linear model, when we are trying to linearize the model, we use this M operator, it's a Jacobian operator, and that's like you just take a different differentiation based on X, Y, Z, the column wise, and you obtain this kind of matrix. So this matrix will give you the idea of the stability of the system. So it is also very important to do like stability analysis in like nonlinear dynamics, or in the climate, they call this singular vector decomposition. There are many ways you can do that. So that's how we do. And then when we do the assimilation, that's how your trajectory looks like. So when we are constructing the trajectory, you can see it follows kind of nicely with the observations. But one thing, if you notice, that we have a very short window. I mean, Adjoint has this problem that you can't go back further, especially with the atmosphere. The reason is that it's a linearized model. So you have a nonlinear model, and then you linearize the model, and you are trying to use that. So to avoid that, like most of the places, they use very short time window assimilation. As I mentioned, that in ECMWF, they are using 18 hours or 12 hours, and other places also is lies in one day. But there is also a way we can increase the assimilation window that I will talk about in our coupled data assimilation part. So that's the thing, or the background of the data assimilation by using 4D var. So now we go into the coupled data assimilation. So the first I talked about the data assimilation, which can take place either in the oceanic model or the atmospheric model or the land model. But coupled data assimilation is basically like when you try to assimilate all the observation in a single model. And that's not easy, because atmosphere has a different time scale, and coupled data like ocean has a different time scale. So somehow to combine all this thing in a single model is very challenging. And I think as far as I remember, the first coupled data assimilation took place in Japan by Sugiura on that 1998 or something, where they use a simplified coupled model, and also it's adjoint, to predict the ENSO. This big ENSO happened in 1997. So the good thing about the coupled data assimilation is that you can use for this subseasonal prediction, or to have a better representation of the Earth system, because all the reanalysis, they have biases. So ERA 5 has some biases, NCEP, they also have biases, and they're also kind of moving towards the coupled data assimilation. So it started in 90s or late 90s. And then again, like I was at the reanalysis conference in Japan, and there most of the groups, they are going towards the coupled data assimilation and how we can achieve that. So this is like we started with the CISM is a pilot project. So what we do is like we take the oceanic data from, okay, there are two things are coming. No, okay, no. You see, we have cursor. So we have atmosphere from ERA 5, and we have like oceanic profiles like EN4 profile, which is I think from Met Office UK, and then we have like sea surface height and other variables, like mainly these variables we used to assimilate in the ocean. And for ERA 5, for the atmosphere, we relied on the ERA 5. And this is a strongly coupled. So I should mention the distinction between, there are two things called strongly coupled and weakly coupled. So in the most of the places, they use a weakly coupled model. So what it does, like they have the atmosphere, it is assimilated separately from the ocean. And after a few while, they just try to change the state in the ocean and then run forward. So it's also done in the ERA 5 as well. And in our this pilot project, we focused on to have a strongly coupled. So we are doing the assimilation simultaneously in both the system. And then what we do, like generally we have parameters like one value, but we just broadcast that parameter in 2D space. So we multiply it. We make one value to a matrix, and we multiply it in each grid point to have better control, to like optimize the parameters into like to get like subgrid processes. And also like you can see here is a tau is a parameter in the MIT GCM ocean, and that's like this boxes are the parameter how it is changing. So you can see there is no uniformity in the parameter, rather it lies from positive to negative. So that's how, like, to have better control, we just broadcast that one. The same with the cloud cover. And the reason I'm showing this particular parameter, because this parameter based on the cloud or the precipitation or like the convective process we have. And if you recall the slide where I showed the CISM climatology, we had a negative bias. So to improve that one, because cloud influences many things, so not only temperature but also like other feedbacks. So we focused on like 14 parameters in the atmosphere and like 4 parameters in the ocean, and also some boundary condition and fluxes. So I'm not going into the detail, but just to give you the essence of this coupled data assimilation. So now we have this thing. This is from oceanic state. So this is like iter 0, like as I said, that's a couple data, I mean data 4 divide is like iterative process. So it is going in a loop to optimize the state. So this is like first state, right? And this is like the 40th state. So first one is the temperature at like 170 meter. You can see there's a large bias in Indian Ocean and in the top here Enso region and in the Kuroshio region. And so, so you can see the bias, the magnitude of the bias is everywhere, and the iter 0. As we go further, like as we go more and more into the optimization process, you can see that we went up to like 40 iteration, and it took us like 1 month. So we have basically we reduce the bias in the temperature profile. And then we also, you can see the salinity mostly in this gyre where we have subtropical gyres. We have this high RMSE in the mainly in the subtropics. And then you can also see at the 40th, we remove the most of the biases, the strong positive biases, but we are still working to improve the biases in our next CISM. And this is the SST bias. This is we obtained is a difference from like hard SST, and you can see at the iter 0 we have this Pacific North Pacific bias, which is kind of resolved there, and also like most of the places is we have less biases. So it shows that the data assimilation things we are doing is actually working because we can reduce the biases.
Yeah, reverse to cold bias, right?
Yes. Now we have some problem in the atmosphere, so that we are trying to resolve it. Because it's we actually don't know how many parameters we need to optimize. So we ran that model and we thought, okay, so these are the parameters. Is kind of interesting. So and then we did it, and then we got this one. And again, we are running the model. So because every time I run, it goes like
cold bias won't be good.
No, it's not good. It's not good. It will have a different kind of repercussion. So that we are trying to improve. And also we have a very coarse resolution. This is the 5-degree resolution, 5.6. So our next step would be like to have higher resolution and to get rid of the biases. So here you can see that in the atmosphere, okay, so there I come to the point, like as I mentioned earlier, the atmosphere is very much unstable in the adjoint when you do. So there what we are doing, we are forcing the adjoint with ERA 5. So by means that we are doing nudging process. So nudging is basically you are coupling, so you do some kind of synchronization with the model state. So synchronization takes place between the observation and the model state with some kind of, you have a tau, like a synchronous nudging coefficient, and that allows you to have a longer scale or longer time scale or time assimilation window. And that's why like we force this atmosphere with the ERA 5. And there's a one problem with the 4D VAR. 4D VAR, from my experience, is becomes very much vulnerable when you have sparsity in the observation. So like we thought to incorporate the real observation in the atmosphere, which we did in the ocean, but from our experience is not working well. So it our next step to somehow combine the filter and the adjoint to have like to assimilate the actual real world atmosphere into our model. But still, like when we see the thing like mainly the fluxes, the top solar radiation, we also somehow reduce the biases. So we have biases in this area. So it lies there's a strong cold bias we have before, and now it has been removed. So the atmosphere, we are removing the biases. And same with the thermal radiation is now is you can see is going 0. And now you see the temperature. Temperature is also, we had a very strong negative bias in that ocean. That's also kind of going down and down. So that's a kind of positive sign that it's working. But it's still, as I said, that coupled data assimilation is it was there, but now it's still we are growing topic. and we are trying to improve the coupled data assimilation thing. So
this is only nudging. There is no adjoint in it.
No, it is there. It is there. So when you do the nudging, you have this nudging coefficient in the adjoint, right?
Okay, so coefficient is derived from the adjoint.
Yes.
Actually, it is
Yeah. So because to damp the adjoint to have like the model, yeah. Okay, now as I said, like I have interest in the adjoint sensitivity analysis. So how we can leverage that sensitivity analysis? So I started with the heat wave thing, the heat wave in India, and I found that this area is pretty vulnerable to heat waves. And I saw many papers where they discuss about the positive trends and like positive, like the high intensity is occurring in this region particularly. So this is like reanalysis. So I first started the reanalysis. I picked up this period 1980 to 2022 and only the April and May and over this region. So first I took this IMD graded data set Tmax, and I first picked up the heat wave indices. So this is the definition of the heat wave. So as there is no uniform definition of heat wave, like so what I did, like I compute the climatological 90 percentile, and I take the like more than when it is more than that threshold for maximum 5 days or more. So that's the definition of heat wave I used here. And here are the composites. So I have reanalysis from NCEP and GLAM for the soil moisture. So this is the composite of the Z200. You can see some kind of wave-like pattern is going on, and that's also corroborates with previous findings there where people mention some Rossby wave source or Rossby wave propagation takes place in this region. So you can see this kind of thing. And we also see kind of like negative anomaly or strong negative anomaly in the soil moisture. So it says like we have very dry soil during the heat wave. So and all these composites are taken like the onset of the heat wave. So it's just like I have 20 or 15 heat wave events. I took the composites of those things. And here I took the U200. In the U200, what thing I found is quite interesting that during the heat wave we have some kind of shift, not shift, like a positive anomaly over India, and that
Excuse me, onset means initial phase at the or the
no when you start, like you have so the starting phase, right?
Not the peak phase.
No. Because I'll explain later like why I took that one. So. But I think like it depends in the definition. So for me, it's just like I took that beginning of the heat wave. So here you can see this black contour is the climatology of the U200, and we have this kind of positive anomaly here. And there is one interesting study by Jha et al. It's published like last in few months ago from IIT Bombay. They connected that the shift of some kind of positive anomaly over India has a link with the temperature trend over this region. So they have some connections in between. So I don't know much about this kind of reanalysis perspective, but what I did, like I took this kind of case study and I use the atmospheric part of the CISM because I'll do the adjoint sensitivity, and when I'm looking into the continental heat wave, it's okay to have only the atmosphere because a plasm also has an atmosphere ocean, which is a mixed layer ocean, is 50-meter length, so it can give you a nice boundary condition there. And it's like a 5 point, this is the resolution we have, as I mentioned earlier. And first I run the model forward for 50 years and I collected all the heat wave using the same definition. And I plot the anomalous situation like Z200 or soil moisture and U200. And you can also see they have some similarity, some degree of similarity with the observations or the reanalysis. So that gives us some kind of confidence. Okay, so our model has this kind of property, the dynamics of the heat wave over India. But after that, what I did, I used the adjoint of the plasm. So first I define the cost function over this region. So we have like 4 grid point, and that's the temperature I took. So I took the area average temperature over this region. So that's why like I took the onset, because I wanted to know the background processes. So I mean, because my intention is to understand the mechanism, the onset thing. So that's the heat wave experiment setup I developed that time. And now I start to go back, and I use like 5 or 6 heat wave events. So like ensemble, I created like 5 heat wave events, and I took a mean and to show the mean sensitivity field. And if you see here, and you can see that is a time 0 as the onset of the heat wave. So in onset, we have a positive sign. So positive means like you can consider the sensitivity as a kind of correlation. So positive means like they have a positive influence. So if you change the field on that amount, you'll have that kind of repercussion on the cost value or the cost variable. So you can, so from the sensitivity of the SST, we see there's a block here, and also some due to the color scale is not visible, but we have positive at the beginning, at the onset of the heat wave. And then as we go back, so because we are going back in time, right, to see what are the, how it is influencing. And as we go back, we see like somehow we have kind of a dipole nature in this region. And the one thing I learned yesterday with the discussion with Professor Cole, that they also found some kind of dipole behavior in the Bay of Bengal and the Arabian Sea, where they have this when they are studying tropical cyclone. So I am not fully explored the how it is working. It's just like to demonstrate how the sensitivity field looks like and whether we can get some insight or not. And then we go at the U wind, the zonal wind in the model. So it's like I took the sigma level at 2. So it's basically like around where we have the subtropical jet in this region. There you can see we have a strong positive sensitivity over India. There could be a some deviation from the geographical location because it's a very coarse grain model. So we are not explaining, expecting to like represent the actual thing, like what we observe in the reanalysis. But still, you get the essence, right? That we have a positive thing, a positive anomaly or positive influence of the E wind at the beginning of the.
You already have some bias in the STJs, right?
Sorry.
You already have some bias in the STJ, right?
Yes. Yeah, but that I found like other models, they also have this STJ problem.
It is shifting northward.
Yeah, it's northward. And also in recent studies, they also mentioned that there is some kind of northward shift is taking place in the STG. So what I
bias, right? That is a trend, right?
No, that's a trend. That's a trend. But in our case, like we tried, and but it's a model configuration. I mean, I can't change the model configuration, so I need to deal with this one. So, but we're trying to go for the higher resolution and see to have more levels on to have maybe a stratosphere and see how it looks like. But basically, like the STJ is pretty much well defined and a very strong band. Even like if you play with any this GFD models, they also have this band of subtropical jet. So this is I don't know anything. So it's a model configuration, but we are trying to do that. So and that's why like we are saying that it's not it can't replicate the actual observation, but it can give you some flavor of the observation of the reanalysis. So this will this sensitivity with this kind of model, you can start at the initial guess. Right. So which are the factors we can look into in detail?
My point is the bias can affect this result, right? That is the point.
Yes, that's true. And also like we have not only in the wind bias, we also have a soil moisture bias. So because we are trying to get rid of that one. So first all this forward thing and it started from the climatology. So we done from the climatology, and then we are tuning the plasm, the atmosphere, and again we'll conduct the similar analysis to see like how it looks like, whether we can resolve this bias. If it is a systematic bias or the model bias, we can't do it. Right? So and it's a spectral model, so it's also a bit difficult to understand or handle that one. So, but still you can get idea. I mean, I'm not saying that we are saying this is the main mechanism. It's a part of the mechanism. It's a extreme event has like different drivers. So the one I am explaining here is basically could be one of the driver. And I'll explain with the forward model, and then let me explain first.
Simulation is just a long-term simulation, or you are doing a type of hindcast simulation? What type of implementation is it?
Distillation. It's not hindcast. It's just like I first have like I run the model forward, and I picked up the high temperature over India. So it's just like a forward simulation I first did.
But based on model, it doesn't have to.
It's not seeing the reanalysis or observation. It's the model dynamic. So that's why like we are saying this only the model dynamic.
Reality there.
No, it's the model. But in the model, we have these flavors like, okay, so whenever we have a high temperature, what is the dynamics of the high temperature? Even your model should have some dynamics, then only it can be used for the reanalysis, right? So there you can see like, and this is the atmospheric part. So it is vanishing pretty fast, but it's still going westward direction. So you have this Rossby wave, Kelvin wave thing is going on. It's going in the left-hand direction or towards the Atlantic. And then I picked up this soil moisture. And the soil moisture, we also see a strong negative soil moisture. So this is also corroborating with the reanalysis, or also it's a very common thing that we have mainly for when you have a dry heat wave, then you have a dry soil moisture. So that is, and I saw some papers that area is most prone to like very dry soil moisture in the pre-monsoon time. So this sensitivity field also giving us like supports the thing we found from the reanalysis. Like there we have like a negative or strong negative sensitivity. So these are the things we found. And so then what I did, like I took one example, like one heat wave event, because the ensemble I went up to 10 days, because not all the ensembles have the similar kind of time span. We have kind of instabilities. So we go like 20 days in behind, and I found the sensitivity is reaching to this SST sensitivity. SST sensitivity reaching to like Atlantic, and you see like the positive and negative box. So they have some kind of dipole nature. And our hypothesis was that we saw some influence from the subtropical jet. Like from the reanalysis, we found the subtropical jet is playing a role. Even we also saw that the reanalysis, the U wind sensitivity also playing a positive negative thing. So subtropical jet is playing a role. And as this SST sensitivity is going towards the Atlantic, so that something is happening in the Atlantic, because Atlantic plays a key role in like modulating the jet stream axis, or like the how it will penetrate to this land or this side. So that's our hypothesis that something is happening in a.
How do you find sensitivity here?
Sorry?
How do you find sensitivity here? Sensitivity analysis mean?
Sensitivity
You're using this one?
Yeah, the same thing. It's just like here I have 10 because it's the ensemble, but in this figure I don't have ensemble. It's only one heat wave event, because it depends on the mechanism of the heat wave. Each heat wave in the model might have different dynamics. As I said, like this is by explaining one maybe one driver of the heat wave in this Indian subcontinent. It's not the 100%. It's 30%, maybe something like that. So
is this for spring season?
I can't say it is because mainly April and May, so it's a summer, I guess so. Because the definition of spring season is also be difficult in here, because I saw some paper they say it is summer, the May, and because then we have summer monsoon, so it's April May you can consider. So in April May we have this thing, and here the hypothesis was that as we go in this direction, so there might be a role of the subtropical jet, which is kind of playing with the or kind of influencing the heat wave to develop. So with that hypothesis, what we okay, so a few things we started as in a hypothetical situations, that we have positive negative sensitivity in the North Atlantic. And this region, especially in this region, we have this African jet comes to India, and this region it goes in this way, and it also brings moisture in the winter to spring as a western disturbance, and all this winter precipitation receives from by this embedded in the subtropical jet. So something is happening with the subtropical jet, or with the Atlantic is playing a role, and this lack of moisture might reduce the precipitation amount, which can have like a negative soil moisture, and that could be a like possible driver for the Indian heat wave. But it's all in as a hypothesis. So then what we did we use this kind of field, this kind of like anomalous situation, which we got from the like this kind of a tripole field, which is very kind of common with the NAO situation. NAO plays a role when you have this tripole SST, and that's been there. So we use this SST, we put up in the February. So, and then we run forward that model for like 2 months, and for April and May. So this is like we take the mean of the put-up state and the mean of the unput-up state, and take the difference and see how it looks like. And due to this perturbation, we see that in the April-May time, we have a positive influence in the this region, where we have most of the heat wave occurs. And here is, you can see the patterns in the Z200. You have this kind of Rossby thing going on. And then here is the zonal wind. You have this positive anomaly in the zonal wind and a strong negative anomaly over India. So that was our hypothesis. And now we are also looking into like, because it is almost 1 month or 2 months of window we have. And that if it is there, if this relationship is there, then we have this leverage to use subseasonal prediction. So if we can do the coupled data assimilation, then we can also do this subseasonal prediction, because this all came from the SST. So we can part of the SST, we have the ocean, so we can see it. And we also need to check all the levels of the SST where we need to part up, because this is only in plasm. So this is like one mixed layer SST. So given that, I would like to conclude my talk. So what I showed here, the like how we can use this intermediate complexity model. So nowadays people are using the climate CMIP model to do many things, like answer this internal climate variability, or many heat wave trend, or many things. So my suggestion is that you can also play with them. I mean, they are very easy to handle. You can read the code, it's very easy. So it's only important, but it's easy to read. It's better, I mean, it's easier than the other fully coupled model like MPIM or something like that. So, and you can get like, you can make large ensemble, you can see how the things have been changed, and you can, let's say you can do the pi control run, or like the double CO2, everything you can do with this kind of intermediate complexity model. And if you have like, for example, in our institute, we have this SISM, this intermediate complexity, this SISM with its adjoint. So that could be, I mean, we right now we are using to test case as an Indian heat waves, but that could be increased to study some more. And we are also trying to do some experiment with the data assimilation scheme. So our future goal is how we can assimilate this sparse atmospheric data into our model, because that's been a challenge, like the sparsity and the irregularities. That's a challenge in the atmosphere, especially with the intermediate complexity model. And the last is that the approach I was trying to show this use this adjoint sensitivity with the reanalysis, because there is a whole part where I carried out the analysis to get understand the heat wave pattern from that reanalysis perspective, because the mask I showed there, the perturbation I showed there, it came from the reanalysis. Like I checked like what kind of SST pattern could lead to that kind of anomalous state. So that I drawn from the reanalysis. So one can combine the adjoint with the reanalysis with some data. You need to understand like which kind of method you can use to analyze the reanalysis, but it is very useful. Like you can combine these two approaches. So that will. With that, I would like to conclude and thank you all. And I have also one request, like yesterday with our discussion that we came across again and again the sparsity of the data problem. And in India, not only India, but many other places, we have the problem with the data. So it would be great, like people here take initiative to have like a repository, so people from outside can also take leverage to understand or download the data to do some analysis with the data over the Indian subcontinent. With that, thank you for your attention.
Thank you, Abhirup. And we are ready for questions.
Yeah, Abhirup, thank you. Very good work and presentation. I have 3 questions in fact. So one is that in your sensitivity runs of adjoints, what is the cost you give, and in what parameter you give the cost?
It is the cost. I mean, you take the mean temperature about this box. So you have 4 area, like 4 grid points. So it's an area average temperature. So that's the cost function. So I mean,
so the cost is given only in temperature.
Only in temperature.
Okay, but in the heat waves are not confined only to temperature. So its expression may be in temperature, but cost can be in the other parameters. Yes. And they can interact non-linearly.
Yes, that's true. But the thing is that
fine. I'm just observation I made.
I mean, just to interrupt you, sorry. When we do the oceanic heat wave, we are also doing marine heat wave with the ocean only model. there we have a set like different kind of cost function.
Okay, fine.
So it depends on because it is only the land heat wave, and I saw like people are using only temperature, but right now we have humidity index and many other index like 5-6 definition of heat wave. So
okay, you could add more costs to see the combined sensitivity.
Sure.
So that's okay. It's a technical question. But my main concern is what you identified can be verified. If you look at the 20-day back SST anomaly of Atlantic, are they having pattern?
Yeah, I did that. So the pattern I got there, actually this pattern, this kind of pattern, right? Okay, so I am just I didn't include this slide. So actually this came from the reanalysis. So what I did, I went back. I'm almost like 1 month. Like for one particular instance, and I went back and I found that the role of something is happening. The intensity of the SST sensitivity is increasing, but I couldn't go back further, because it shows in our experiment it's almost 2 months, and after that I tried to damp all this noise and all this gravity waves, but still like 1 month is for the limit. So what I did, I took help from previous studies. Like there is one study by Kiran Hunt in the Reading, I guess. So what he found that the some dynamical change in the Atlantic is influencing the subtropical jet track.
No, I'm not. That may be fine. That's not my question. I think you did not get my question.
Okay.
So in your sensitivity, you picked up anomalies on Atlantic. In the
I mean sensitivity field I got is
So can you go to that? So then you come up with the idea that
here, right?
Yeah.
This one.
Yeah. So did you check this with the reanalysis 20 days before a heat wave? Are you getting it?
Yeah. I mean not the exact way,
but in any way near.
Yeah. You have a strong in this positive here.
Okay.
Like mainly from my experiment, I found that when you have this kind of dipole pattern, not most on the Greenland is effective, but mostly in the 5 to 20 degree positive, and after that in the Gulf of Mexico and that area, if you put a negative anomaly, which is observed from the SST anomalous state, right? So it is there. So you have sometimes it's not that much significant. It's like 90 percentile significant, but you have this kind of hot U-like shape. So
before 20 days of the heat wave.
More than 20 days,
more
like
than
almost
20.
2 months ago. Yeah.
2 months ago.
Yeah, 1.5. So it's 90 days I found.
Oh, okay. So. Okay. The third question is this. Okay, understanding from the model, but this is still will be the model mechanism, because I see the reanalysis comparison of your heat wave. If you go several slides back, so the structure, this one.
Yeah.
These have wave number 4 or 5 in the zonal, but in your model is wave number 2.
2, yeah.
So that can make a lot of difference in the. So what you are identifying is still model.
Yeah.
So only way out perhaps maybe to improve your resolutions and bring up this many wave number in your model. Then we do the sensitivity will be good.
Actually, that's a very nice point. Actually, we found the heat wave in India is associated with it. The Rossby wave number lies between 5 to 7, right? So that's the typical an average you can say. And when I went with the high resolution, like we have 2 degree resolution plasma atmosphere, and there we have 5 wave number, and there the problem is that as you increase the resolution, you are increasing the disturbance. Like when you are going back, if you have a high resolution, you have more instability. So there I need to damp the many other parts. So that's I am doing, and so that's maybe in our revised version we will have it. So it's just a test case, like how one can utilize the adjoint system or adjoint sensitivity. If you have one adjoint model, you can just use that one in a different perspective. So that's a showcasing stuff. It's not like we're saying. And also like when I confirm this kind of mechanism with CMIP model, and also MPIM, you might know the Max Planck medium model, with the similar kind of perturbation, they also have this mechanism with the CMIP 6 or something. So the mechanism, it's around explaining 25 to 30% of the extreme or heat waves occurring on this region. So our saying that the mechanism we are explaining here is just giving 1/3 of the whole picture. So there still we have big players. We are explaining like 70%, which we don't know. So it's just one example. So that's all. Thanks.
Yeah. You have any more questions? I have, yes.
Last.
Okay, I have two questions. When you say that this is the CSAM is the model of intermediate complexity,
Yeah.
it means only atmosphere and ocean, or you have other components as well, like land, sea ice, and
We have one,
BGC.
yeah, we have land, which is like a bucket model. So it's a small, it's a kind of standard low resolution bucket model we have. We also have a sea ice. So MIT GCM has a sea ice, and our Plasm also has a sea ice. So I think we are using MIT GCM sea ice. So we have different components. So, but when we're assimilating only the atmosphere and the ocean. So yeah.
Okay. And one other question, just
Yeah.
correct me if I'm wrong.
Yeah.
This is sensitivity analysis,
Yes.
which means you are trying to find the dependency, causation basically of
Yes.
one,
Yes.
the
Yes.
parameters
Yes.
driving
Yes.
something.
Yes.
So there is something called PCMCI.
Yes.
I'm sure you are aware of it. So that might also do the same thing with additional constraints, like you will be able to take all these variables into account at the same time, right? So
Actually, the thing is that PCMCI, I mean, we wrote a paper, I mean, we are going to submit a paper on that one because the person who did that one is also in our group. So he was the PhD student of us. We belong to the same supervisor. So we did that one. And then the problem is that PCMCI is also pretty susceptible to many things. You know, if you increase, if you just don't, if you don't remove the trend well, then you will have some bias. If you don't do the anomaly well, you will have some bias. So PCMCI is efficient because like we also did a PCMCI work on that one. But PCMCI, you need to keep many things on your mind. So to do the anomaly thing or something like that. So PCMCI is good when you do an offline experiment. It's very efficient. You can do, and I think PCMCI is mostly linear stuff is giving you, and they also have the trigonometric non-linear thing. But in the adjoint, is mostly is linear. It's not giving you the non-linear perspective flavor. But yeah, PCMCI is a tool you can do for the causation. So yeah.
I tried it I work on ocean biogeochemistry, so I use nutrients and other biogeochemical variables to just see the causation.
Yes.
But I found that the source of these parameters also make a difference in the PCMCI result. So
even they have this false neighbors or false connection filter. So you need to be very cautious about while you are like making a hypothesis, right? So while I was doing something and then I playing with the CGT. You know, we have this CGT thing, and I found okay, I got influence from many other factors, and that's not useful because when you do simple correlation, you will also find many parts or many significant points which are not relevant. So that's a caveat we have in the PCMCI. But what above all, it's a very good toolbox, and they have a really nice documentation you can use.
Because you have all the model variables, I thought it would be very straightforward for this.
Yes,
I was stuck there.
No, I did that. So I tried to combine these two things, so PCMCI and adjoint, and the length of the paper went so high, so I just chopped down and just making 2-3 more. So that's
Okay. Thank you.
I have many questions, but I'll ask one or two only. See, in your adjoint model, from different iterations, from the first, in the beginning, there was a lot of differences.
Yes.
But then in 40 or 50 iterations, it has gone, right?
Yes.
How did it go? So what is the...
So like when or each iteration, so your model is going back, right? And you have the gradient of the cost function. So in the gradient, you have like positive, negative, like it's a kind of direction. You have kind of, what is this called? You have profile, or what is the cost profile? You have this gradient descent algorithm thing, you know, like you find the minimum. So you optimize some parameter or initial condition, and then you try to find minimum. So it's like every time in each iteration, it tries to like...
It's a conjugate gradient.
Yes, conjugate gradient.
I think this is a Newtonian descent.
Yeah, Newton descent,
Slowly.
Yeah, it is. But then again, you said you also nudge with error phi.
Yes.
So that is a... See, normally in adjoint models, they don't nudge to reanalysis, right?
Yes, that's true. But actually, it started by Abhirup. There's a guy in Switzerland or Sweden. They found that if you nudge that one, so nudge is basically, for example, if I talked about this example. Let's say you have this simple Lorentz system, And here you can add like plus alpha into observation, right? So that's your nudging, simple in the forward model, right? And then when it comes to the adjoint, that nudging parameter will be there. So it is kind of damping the adjoint.
Yeah, but that is again that it's not a fixed nudging weight. The weight of
no, that is not weight. That is nudging factor coefficient he's saying. That only decides how much when it has come back to the observation.
Yeah.
So that has nothing to do with the adjoint concept.
That time scale of nudging tau may be coming from
this may be. I mean, you may be knowing that you are nudging in daily time scale or what time
so our nudging is a daily time scale.
Yeah, so that is what the question.
So this is basically like what we do. We use some exponential divergence thing and find the Lyapunov of time. So that's the divergence time we find, and tau we derive from there, and then we plug that fixed tau.
Now, how do you rule out that the iterations, different iteration improvement is coming from nudging or not?
No, actually, like nudging is kind of constraining your atmosphere only. We don't have nudging on the ocean. And what you said, like how we are confirming is just like we're trying to achieve the similar state as era 5 in the atmosphere. So what we are observing, the atmosphere reduction in the parameter, I mean the bias reduction is based like as we have that goal. So we are not bothered about whether it is coming from nudging or that thing. So that's why.
But it's a coupled assimilation, right?
Yes.
So then ocean will respond to that.
Sorry?
Ocean will respond.
Yeah, ocean will respond. It's just like you have the flux exchange, how much is there. So if, for example, in our model, when I started that time, we didn't have proper ENSO, right? So when I just nudge with the era 5, without adjoint, just nudge for one model, then we had the ENSO. So basically, we saw like the exchange of the temperature or the flux exchange, what is happening between the atmosphere and the ocean is not communicating well. So that's why we thought, okay, so we nudge that one, and without nudging, we don't get to use the large assimilation window. And the reason we want to use large assimilation window because we want to have a few decades for the decade. I mean, the parameter or the model should see few decades to optimize the parameter. Then only it will be useful for the decadal prediction. So that's why, like, we use the nudging one to.
But suppose you nudge and you get the ENSO.
Yes.
Okay. How do you predict? How do you make a critical prediction?
So right now what we are doing that after 40 iteration, we have set of parameters, and then we have like also some say correction in the boundary condition. And when we are running the model for like 1 year, that time we are not nudging. That is free run. So that's with the optimized parameter and some flux correction from the climatology. That's all. So the thing we are optimized while we are doing the optimization, that time we are only using the nudging time. Otherwise, it's
how this information will improve your prediction.
Prediction means like it's changing the parameters. So it's optimizing the parameters. So if you look into the parameter, I mean, I don't have the parameter plot here. You can see it's when we are when we did the assimilation with the era 5 with nudging, and then we at the last step when we obtain all the parameters, they actually improve the mean state of the system. So as we are kind of hoping to get similar kind of atmosphere like era 5, so that's why we are doing on that aspect. But maybe you are saying that how we can achieve the forecast or the prediction. So for the prediction purpose is like we use these modified parameters and to see how far we can go. So that's the one.
Okay, now, normally in these nudging experiments,
yeah.
See, for example, you said you could reproduce ENSO. So they do it by nudging only over the Pacific.
Yes.
And then they make the Pacific ENSO representation right,
yes.
And see how the teleconnections are captured in the model.
Yes.
So, but not for forecasting.
Yes.
So that is mainly for process understanding.
Yes. That's a different thing. Even like in our group, they also do that one, nudging only. They mainly interested in the dynamical perspective, right? And in what we are trying to do, let's say when we do this assimilation, we forced by the atmosphere, and then we have the parameters, and then we run for 1 year, let's say, and see how much we can do the prediction. Because in the nudging scale, nudging is basically you are tuning your model state to act similar or be similar with the reanalysis, right? And that could be useful for 1 month or 2 months. I mean, you can do that one. So once you stop nudging, and you can go like further, like 2 months maximum. But if you have some kind of optimized state, if you already have a parameter optimized, which kind of mimicking the real world scenario, and then if you don't do nudging, you just simply run the model, then you still have a good state, so good atmospheric state. So while I was doing the heat wave experiment, so what I did, like I was trying to do kind of prediction, like the temperature prediction or something like that. So there, let's say I have my state nudge, let's say I'm running from January to March. That is nudged with the optimized parameter, right? And at March, I stopped it. So April and May, the prediction I'm doing, it's free. So though my state, the initial state on April is kind of improved or kind of modified due to the nudging, but after that is purely like solely depend on the model configuration. So that's what we are trying to do. But it's not. But we are not focused on the prediction right now.
Yeah, but that in a way we have in one of our experiments.
Yeah.
We used even 3D VAR.
Yeah.
So we tried to nudge even the atmospheric profile.
Yeah.
Up to April, May.
Yes.
And then we saw that the summer monsoon forecast has improved tremendously.
Yeah.
So because the model land preserves the memory, and so that improves the forecast of monsoon rainfall.
Yes.
But even otherwise, it is very difficult to get the monsoon. Right?
Yes.
So if you nudge it, so you get. But I don't understand here what the adjoint thing is doing.
I don't know.
Yeah,
so
because
I'm also yesterday I thought
that is
some weight is coming, but
that's a concern.
Yeah.
Whether it is done by the nudging, or by the adjoint.
Okay.
That is the.
Okay.
That's the point. You can do different experiments with the only nudging and see whether what type of improvement you are getting.
Yes. So what I did, like I have like two setup. First, when you are doing only ocean, you no need to do nudging. You can just use like course resolution, and because it's linear, you can just simply based on that adjoint, and you can estimate the state, and you can do some forecast. I think Gecko reanalysis also is, or Echo reanalysis also is done like that way. But when we are doing this kind of, because it's a pilot project, I mean, it's not like we are saying that it's all, right? You are trying to show the capabilities of these things. So what we try to do, first, we try to have a long assimilation window to optimize the parameter, because we are focused only on the parameter estimation or like tuning the model, or to have like good mean state. So to do that, or to have like better representation and to have a long assimilation window, we are nudging the atmosphere only to have just to achieve this long assimilation things. So with nudging, without adjoint, you can do forecast for 1 month, and again you can do nudging, and again you can do forecast. So that thing is not new. I mean that.
But whatever you are doing, you are only improving the state.
Yes.
Not the basic.
No.
Basic. See, the bias you are not removing. See, bias is still there. You saw that in because of your model, there's a large bias.
Yes.
It's more than 6 degree warming and cooling. So that,
So that bias, what you said, that we figure it out, is mostly coming from the, like in SST, is mostly coming from the eddies. So the eddy resolve is also a challenge that what we try to achieve is like to see how the coupled data assimilation looks like in this kind of model, and then we can follow with the high resolution like ICON or MPIM. So like every data assimilation institute.
Anyway, I think these are, you need to work more on that. And
because it's.
But anyway, the sensitivity experiments look nice, but then you have to come with the processes.
Yes.
You know what processes are. Because whatever you are saying, it's already reported.
Yes.
The dryness of the soil, or the meta-dross waves. These are all.
It's all there.
All there.
Yeah.
But what more? These experiments can give. So that way processes you.
So the hypothesis we have till now is not published. So it's like we're still working on this manuscript. So we have first we started with the adjoint, which gave us these variables. It's not even giving us any concrete proof. It's just giving us some things we to look for, right? And then I went back with the reanalysis. I used like NSEP or ERA, these two reanalysis data, and I followed some technique used by like EUF analysis in this correlation analysis. So what we observed that the subtropical jet during winter times, like winter to spring, it is kind of modulated by the Atlantic SST, right? And there is a paper by this Kiran Hunt I mentioned. He observed that the high PC or the PC of the UF, whenever positive values, it goes like it shifts the subtropical jet thing. That was his hypothesis. But he connected only with the western disturbance. And our hypothesis, which we found that in this February-March time, some dynamical changes in the Atlantic, which we got flavor from the adjoint thing, is also has some repercussion on the high temperature. So our adjoint analysis and also the reanalysis analysis, we are mainly trying to focus on the preconditioning of the heat wave, because as we are going back, so we are mainly dealing with that. So what you said that most of the things have been reported, so nothing new is there. We are not saying we are saying something new. It's just like we are focusing on the preconditioning. So something happened like 1 month before in the Atlantic, which is kind of driving the subtropical jet, which is this moisture from Arabian Sea, from the Caspian Sea, something like that, which are linked to the precipitation, right? So it's like multi-layer processes going on. So you have something in Atlantic which is changing the precipitation pattern or the moisture pattern, which is drying the soil. And when you have a dry soil, it can initiate the adiabatic heating, and that can give you some like anticyclonic flow, and that's the onset of things. So that's the thing we are trying to report. So yeah.
Okay. Thank you.
Any more questions? Okay, if not, thank you, Abhirup, for the talk, and thank you all for your time.